On the other hand, you can also stop making that face and just hand it in like
Wait, hold on.
Okay, friends. Page 101. Last day we were looking at delta G is equal to delta H minus T delta S, and we had looked at situations. What? This is the blue book, page 101. Blue book. I think tomorrow I will hand out your next workbook.
Are we supposed to have that?
This review, yes, you should have this review. If you did not pick up the review, come grab yourself a copy. I know that most of you have tests tomorrow and probably are going to do nothing with it tonight. That's fine. Just have it on your person, right? Then you can use it at any point you want to. Pardon me? I do. What kind do you need?
The
Apple or USB-C? USB-C? There. Sorry? Yes. No, they're like in a tangle.
What? They're in my contact no accident.
Okay, this is a question I have actually seen in AP. So, how would it be possible for a spontaneous or thermodynamically favorable how could it be possible if we have a thermodynamically favorable reaction where delta H is negative and delta S is positive, and that gives us a delta G, which is, if delta H is negative and delta S is positive, what does that give us in terms of our delta G? It'll be negative because remember, it's minus T delta S. 101.
Oh, what?
Blue book. Okay. How is it possible then that we can have a spontaneous reaction that does not proceed? So say, for example, this piece of wood here. If I were to burn it, yes, if I were to burn it, it would, is that an endothermic or an exothermic reaction? Burning. You guys are killing me. Exothermic, because it's fire, energy comes out, yes? Okay, so exothermic, is that thermodynamically favored or not favored? Favored, okay. Now, if I burn this, do you guys know the products of combustion? Carbon dioxide and water, and you'll get some ash as well, okay? Now, which one is more random, a piece of wood or carbon dioxide vapor, water vapor, and ash? Which one's more random? The vapors and the ash and the whatever. Okay, so entropy says go forward, enthalpy says go forward, and yet this wood is not lighting on fire. Why not? There's not enough energy. What kind of energy do we need? We need the activation energy, yes. Okay, so even though it is thermodynamically favored, it's not kinetically favored because the activation energy is too high. So I think that may be the reason why AP is moving away from the language of spontaneity, because that sounds like we should have spontaneous combustion, right? But it is thermodynamically favored, but it's not going to be spontaneous because the activation energy is too high, okay? So it is not kinetically favored. Is good? Now, we could get it to go if we provided enough activation energy, and then it would go nice and spontaneously, right? And it would go to completion, right? If the fire gets going, as long as that activation energy stays there, it will go to completion. All right. What if the driving forces oppose one another? Well, we're going to get some kind of an equilibrium. And so what's going to happen is that temperature is going to be the deciding fact on whether delta G ends up being positive or negative. So if temperature is big, then the T delta S term is going to be important. So if temperature is large, T delta S is important, right? Because T makes that term a large number. Yes? If temperature is small, then the T delta S term, the minus T delta S, will be unimportant. And what will happen is the delta H, the sign of delta H will dominate, okay? And once we go through a couple of examples, I'll give you an example of what they might actually ask you on an AP exam, okay? So if the reaction is exothermic, so we have a negative delta H, is that favorable or unfavorable? That is favorable. And if we have a negative delta S, is that favorable or unfavorable? That's unfavorable. So we're like, oh, hey, hang on. Am I going to favor my reactants or my products? It depends on which term is larger. So what we have right now is we have delta H is negative, so that gives us a negative term here. And then we have, whoopsie, the minus T delta S, which ends up giving us a positive value. And what do we end up with? Do we end up with positive or negative? We don't know because it depends which one is bigger. Yes? So if temperature is low, T delta S is going to be small. And so a negative delta H will become the more important factor, and you'll end up with a negative delta G. Yeah? Now, if you're given actual values for delta H and delta S, you can chuck them in there and numerically prove that it is that way, okay? It's possible that even with a low temperature, if you don't have a very negative, like if you've got a small negative delta H, it's possible that it could still not be favorable, but this is just in general, this is what it would most often be, okay? If temperature is high, then T delta S is going to be large. And what that's going to do, and if you remember, we had here a negative delta S, so that's going to be a negative, so that's going to be a large positive. Okay, so we have a negative, we have a large positive, and that will lead to delta G being overall positive. Does that make sense? Okay, one person thinks it makes sense. Anybody else think it makes sense? Okay, several of you. The rest of you, I don't know if you're paying attention or not, but there we are. Okay, all right. Now, if we have an endothermic reaction, I don't even know if it's worth going through these individual examples. We're going to do it just for completion's sake. If we have endothermic, then we have a delta H, which is positive, and then we have a minus delta S, which is positive. So if it is endothermic and entropy increases, then both of those are positive values. So what we end up with is we end up with a positive value and a negative value, and we don't know what that equals again, right? Because they're pushing in opposite directions. So if they give us numbers, that's wonderful. We can just figure out what it is. But in general, if temperature is small, then you can say, okay, delta H is more important. Delta H is positive. So that is unfavorable. So probably delta G is going to be positive, non-spontaneous. Yes? Hang on one second here. Okay. Ooh, this is a good question. Under what conditions would the following reaction be thermodynamically favorable? Low temperature. Low temperature favors the forward reaction. Because we have delta H is negative, right? So that's a good thing. That's favorable. And delta S is positive. Hang on, is it? No, delta S is negative. Therefore, negative T delta S is positive. And so in order for our delta G to be negative, we would need the temperature to be small. There's another way to think about this question as well. What happens if you decrease temperature? This equilibrium shifts to the right, which means KEQ gets bigger, which means that favors the forward reaction more. Yeah? Okay, so your homework tonight is to go and study for whatever it has you have tomorrow, because who am I kidding? You're not going to go and study chemistry, are you? you are going to ignore it regardless. If you don't have tests tomorrow, you can start working on the review. Okay? Tomorrow we are going to finish up the AP stuff.
Okay, and then on Friday.
And then on Friday, we're going to be starting Unit 4.
Or
I know.
with 3.
Where did 3 go? 3 is going to come after 4. I should really renumber the whole thing, but it would require me to renumber every single document.
Okay.
And I'm like, I'm